Hi, Miss Figueroa here. It's October 13th, and today we'll be doing transformations of quadratic functions. So we just did our introduction to quadratic functions yesterday, and we talked about how once we're in vertex form, that it's easy to see those transformations. So today we're going to be talking about those transformations that we briefly touched on yesterday. So a transformation changes the position or size of a figure. So we've got three different types of transformations. We have translations, dilations, and reflections. So translations are the ones that we call slides, moves left or right. You can move up and down as well. Dilations is probably new. And dilations are going to change the size. So they're going to change the width of our parabolas. And then reflections, we know that's where it's going to flip across a line or an axis. So those are three different types of transformations that we can have on a quadratic function. So translation is going to move up, down, left, right, like I said. So an example would be if we had y equals f of x plus 3, where f of x is the original function. So we're taking that original function and we're moving it up 3 units. So if we look at that bottom there, so similarly, y equals f of x minus 3 would produce a new parabola shifted down 3 units. So up 3 units, down 3 units. So up is positive on the end, down is negative on the end. And then for our left-right movement, we would have f parentheses x minus 2 or f parentheses x plus 2 or whatever number. And if it is minus, it is to the right. So this one's going to be kind of the opposite of what we would expect, just because, well, let me write y equals, just because with our vertex form, remember we have x minus h. So since it is minus h, we got to take the opposite. So if it is going negative, then really we're moving to the right. And if it is going positive, then really we're moving to the left. So just be careful with those left-right movements. A dilation is going to make the graph narrower or wider than the parent graph. So if a is greater than 1, so if we have a number greater than 1, then it is going to be stretched vertically. And if a is a fraction, then it is going to be compressed vertically. So the way I like to say this is a fraction makes the graph look fatter. I know it's terrible. I know it is. But it helps y'all remember. So if there is a fraction for a, then the graph will look fatter just because it is compressed vertically. So I like to imagine we have one of those cartoon hammers. Let's say we had a really tall person, and then he gets hit on the head with that cartoon hammer. You know, in those cartoons, then he ends up being, well, he would be wide. He ends up being like this wide guy who's been squashed. Please don't laugh at my drawings. So think of the fraction as that hammer that's going to make him wider. And then for the stretch vertically, I like to think of if you were holding a rubber band in your hand and you pulled on the rubber band as hard as you could, the harder you pulled that rubber band upward, if it started like this and I was holding it right here, if I pulled it upward, then I'm going to have this stretched vertically where the point is still upward and we're still pulling. So just be careful with those where we know that if it is a whole number, then it is stretched vertically, and if it is a a fraction, then it is going to be compressed vertically. So on the example, describe how the graph of d of x is equal to 1/3 x squared is related to the graph of f of x equals x squared. Well, I see that 1/3 is a fraction. So since 1/3 is between 0 and 1, or we can say that it's a fraction, then the graph of f of x equals x squared is a vertical compression of the graph y equals x squared. Then example 2, if we have 2x squared, then that is going to be stretched. So we have a stretched up, this should not say, and then translate it. So ignore that part. I guess it was edited and then not edited all the way through. So just looking at the dilations, if it is with a whole number, that 2, it's going to stretch vertically. And then we have our good old reflections. So that flips a figure over the x-axis or the y-axis. So the graph of negative f of x is a reflection of the graph of x squared. So if we're taking that original function and we put a negative in the front of it, then it is going to flip across the x-axis. And if we take that original function and put the negative inside the x, then we are going to flip across the y-axis. So these are a little difficult to imagine. So just bear with me when we go over those more in depth, that when the x gets the negative, then it is y. When the whole thing gets the negative, it's x. So we've got horizontal translations, vertical translations, reflections, and dilations. And here are just some examples where you can see it, where the horizontal translation is going to move left, right. And remember, it's going to be using the opposite. So since it is x minus h, we're using the opposite there for left-right movement. Vertical translation is probably the easiest one because that's that k on the end. And so if it's plus, we're moving up. If it's minus, we're moving down. So it's going to be exactly as you think it is. Reflection is probably going to be the most difficult. So we've got a is greater than 0. The graph is going to open up. Oh, this is just whether we're flipping over the x-axis only. And then, so this is x-axis reflections. And then for dilations, that's where we're looking at whether it is a fraction in the front or a whole number. So a whole number is going to stretch, and then a fraction will compress, and that is vertically, so up and down. So on 1 through 4 here, we're going to state the transformations from the graphs and we're just going to state the transformations without graphing. So just looking at the equations, this is exactly what I was talking about yesterday, where we're only given the equation and we don't actually want to graph it. We just want to look at what the transformations are based on the equation. So from the parent function, my parent function is x squared. On number 1, there is a lot that has changed here. So first, we have a fraction in the front. Fraction in the front. Let's see, how many changes do we have? We got 1, 2, and 3. So the first change, fraction makes a vertical compression. It's going to make our graph look shorter and wider. 2, we have x plus 1 squared. So if x is plus 1, then we have a -1, -5 for the vertex. So moving from 0 to -1, I am moving to the left. So we have a left translation. 1 unit. And then the third transformation we have is at -5. which is a down translation, 5 units. And then for the domain and range, remember domain will not change. And then the range depends on the vertex. So normally the vertex is at 0, 0 for the parent, but we moved down to -5. So now my lowest point is -5, and then we're going up toward infinity. So I'm not going to graph these. I'm just going to do the transformations in the domain and the range on each. So then on number 2, we have -1/3 x plus 2 squared plus 7. So the changes that I have, we've got 1, 2, 3, and 4. The first change I have is that negative, which makes a reflection across the x-axis. The second change that I have is that 1/3, which is going to vertically compress by a factor of 1/3. Then on the third transformation, we have plus 2. Remember, plus moves left. So we have a left translation, 2 units. And with that k, that last piece on there, we have plus 7, and that's going to be just as we think it is. So up translation, and then that's 7 units. So we have a vertical translation up 7 units, and we have a horizontal translation to the left 2 units, as well as a vertical compression by a factor of 1/3 and a reflection across the x-axis. So on number 2, we've got a lot of transformations happening. Now domain will not change, and then our range depends on our vertex. So our vertex would now be -2. We take the opposite of what's in here, and then take the last bit as it is. So 2, 7 is my vertex. So 7, from 0, I've moved up 7. So my range now starts at 7. But here we have a problem, because this flipped. So I'm no longer like this. I'm like this. So 7 is my highest point. So 7 will no longer be the lowest point. My lowest point would now be -infinity, and it's going all the way up to 7 and then stopping and turning back around. Number 3, we have 3x minus 4 squared minus 2. So we've got 1 change, 2 change, 3 change. So the first transformation is that 3. So we have a vertical stretch by a factor of 3, which means the graph is going to look taller. Then we have -4 on the inside there. So remember, on the inside we take the opposite. So -4 will move to the right 4. So we have a horizontal translation to the right 4. And then -2 on the end there for the third transformation is going to move down 2 units. So my vertex now is the opposite here, so +4, and then the last part as it is, so 4, -2. Domain will not change. And then range, this is still facing up. So we have a parabola facing up, which means -2 is my minimum. So -2 to infinity. Then on number 4, we have -x minus 2 squared plus 6. So the changes, I have 1, 2, and 3. First change is that negative, so we have a reflection across the x-axis. Second change we have is that -2. Remember, on the inside we do the opposite. So -2 will be to the right 2. And then the third change is +6. On the outside we do it as is. So +6 would be up 6 units. So we have a reflection across the x-axis. We have a horizontal translation 2 units to the right, and then a vertical translation up 6 units. So for my domain, it's not going to change. Then my range again depends on the y value of the vertex, but I have this negative here. So I'm negative, I have a frowny face. So negative, we are opening down. So my range, my y value will be a maximum. So that vertex is the opposite. So +2, so +2, 6. So that y value of 6 is the maximum. So we're going from -infinity to 6. So that is it for today's notes. Make sure you get to that assignment, and then I will be back on this video for the next time we have notes.